Okay, welcome to the third lecture on the lecture series on the future of AI, self-supervised learning and foundation models. Right? So this is where we learn about the fundamental and deep revolutions occurring within AI right now. And it's going to change everything, right? And you heard it here first. So I promised today we were going to cover ChatGPT and Stable Diffusion, but we're going to cover only ChatGPT today because it's going to take up the whole lecture, and I think that'll be a lot of fun and to spend some more time on it. So to quickly recap a little bit what we've done in the previous lectures, right? In the first lecture, we had a high-level introduction. We talked more about the philosophy and history of self-supervised learning and foundation models. Then in the second lecture, we went through all the different algorithms, right? And kind of to summarize this, self-supervised learning learns from observation, right? No labeled data needed. And the meaning that we get is the relational meaning, right? So we learn what a dog is by the company that a dog keeps, right? We learn it to contrast and correlate with other concepts that it appears together with, right? That a dog is something that's walked by an owner with a leash, has an antagonistic relationship with cats, right? Chases and catches a frisbee when those are thrown, right? This is what allows us to understand what a dog is. Not your parents, not your feelings, right? And we really said this, fundamental world model that allows us to understand how the world works from just observations is so important. Because supervised learning, right, when we try to label everything with examples, it's too expensive because it's very expensive to get labels on everything and doesn't generalize, it doesn't learn well. And reinforcement learning, right, if you're a blank slate, you have no understanding of how the world works, you spend all your time exploring nonsense, it will make no progress. And it's very dangerous to learn by interacting with your environment if you have no understanding of it, right? You won't survive long and you won't make progress, right? So that's why self-supervised learning is so important, and it's feeding all the breakthroughs that we are seeing because you can put this model everywhere as a starting point. And it's exactly what ChatGPT does as well, and as we'll see here. And again, like now we are going even deeper into engineering, right? And I want to kind of remind you that there's a difference between understanding the high-level concept of something and how it might be useful for your life and like affect the world at large, versus actually building it from the details up, right? In some sense, you can know what a car is, how it helps you, how it's changing the world in some sense, without being able to build that car. So keep that in mind. That a lot of things here perhaps are not eternal truth, but more kind of conditioned on the hardware, etc., that's available right now. But it's of course very, very hard to understand what's the most important aspect and what's kind of conditional on our contemporary kind of availability of things, right? All right, and so a little bit of kind of the last philosophizing that we'll do in this lecture is just to tie back a little bit to previous lectures as well, that I do this all the time, and it's very tempting to be like, well, in engineering with all these details, right? Oh, these are the most important things, or try to summarize all these things into simple rules. Like this is how you build ChatGPT, and we all try to do that because we're humans in some sense. But it's also very dangerous because what we learned in previous lectures is that actually the best way to learn about details and things, building things, or like, is to expose yourself and get more familiar with it. Try sometimes to resist, simplify everything. Try to just expose yourself and build intuition, right? That's why AI is so powerful, because it builds intuition. It gives up summarizing everything into simple rules, right? So if you don't understand everything here, that's fine. We just get more and more familiar with this concept by exposing ourselves to them, right? And I also put this quote here, which I think is very interesting. So this is from a famous general from I think it was the 17th century or 18th century or something. And he says, pity the theory which sets itself in opposition to the mind. So this guy is a general, right? He's been in a lot of wars, and he's writing a book on war, actually. And people try to reason about war, applying rules to summarize how war is done, how it works. But he says, like, actually, I'm a general, I've been in real wars. They're so messy, they're so chaotic, because there's human beings struggling for their lives. Like, there are no rules to summarize war. Every situation is unique. So that's the first point he makes. And then he says also, like, actually, the mind of a soldier and human beings are not conducive to reasoning by rules. If you put them in life and death situations and have to deal with all the chaos, they get, it's dangerous to reason by rules. They're fooling themselves in some sense. They need intuitive, quick, flexible ways of reacting to their environment and acting, right? So like, not only are rules not true, they're dangerous. You got to be reactive, fast, adaptive, which is exactly what we talked about, what AI is solving for us and what it's good at in some sense. And it's a little bit like Mike Tyson's quote, right? Everybody has a plan until they get hit in the face. And it's a little bit similar. So, just keep that in mind in the lecture as well, as I kind of push certain rules onto you. Like, maybe that's not the whole story, right? All right, so let's get started. ChatGPT, right? This amazing chat bot that solves so many tasks for us and has an amazing master of language, right? And is taking the whole world by storm in some sense. Seems almost magical. And it will be a lot of fun because today we're going to kind of go through all this and dissect it and see, is it actually that magical? Is it perhaps not as smart as we think it is? But also, does it perhaps have huge potential because it is so simple to scale up? And the question is like, how far can we push these concepts? All right, so let's start with just breaking down the actual kind of name, right? ChatGPT. So the chat part is pretty obvious. It stands for just chat, like a chat bot, right? But GPT stands for Generative Pre-trained Transformer. And we're going to break this down because it's broken down into basically 3 different aspects. So first we have chat. This is just a chat aspect. We'll talk about it later. And then we have generative pre-trained and then transformer. And we'll start talking about generative pre-trained, which I also think is the most important aspect. I think actually like the lengths of the concepts here correspond to how important they are for ChatGPT. So we'll start talking about this aspect first. All right, so what does generative pre-trained mean? And it just means what we talked about before, basically. That we learn by just getting text from the internet, right, a sequence of words, and we train now this model to predict the next word based on previous words, right? So maybe I just download some text from online, and it's the text, I went to the financial bank to deposit money, period, right? Now the model trains on that, and it does it word by word. So it starts off just getting the brain right here, the model, the computer, inputs and digests I, and then it tries to predict the next target, right? And right, also to just make it clear, like, it doesn't have the target. Like, we only know the target, so it has to guess somehow without knowing. So if it's wrong, we'll say like, well, this is bad. We give some kind of negative feedback. Hey, don't do this again. And when it's wrong, and then when it's right, we give it some positive feedback, saying, great, keep this up and do more like this in some sense. But of course, it's a very simplified scenario. Let's go to the next one here, right? What we really do when we want to predict I went, the target here, there's a lot of, incorrect ones and only one correct one. So maybe you want to allow the model to guess kind of more than just twice or once, right? Or just give it, you want to be able to use as much information as possible from this training example. And you want to be able to say that, yeah, this is the correct one, but it's also very useful for the model to know about all the incorrect ones, because it also allows us to understand these are not relevant in this context, right? So we might go through, a few different correct ones that it might score or guess, right? Then we give negative feedback. These are not relevant in this context. And then when it actually gets the right one, we say, great, this is the correct one. And we use this example now more, we use more of the information somehow. We convey more of the information. So how this really works, right, is that we want to use as much information as we can from this example, which means that we're going to say, tell the brain to basically, right, the next example, when it wants to predict the target of I went to, it generates a score for all the words in the English language. Sounds ridiculously expensive maybe, but it does, right? And there's ways to speed this up, but it does generate a score for each word, and it's a probability distribution, right? So that's a sum to 1 and be positive. But it's basically a score of how likely they think each specific word is to be next in some sense, right? So it doesn't know, so it generates this scores and distribution over all possible words. And then we say, great, now that we've done this, we can actually point to say that the is the correct one. So now, a neural network has tons of parameters or neurons, right? And it configures itself. Then we basically say like, hey, actually, change your parameters and your neurons a little bit. So the next time when you see this example or something similar, right, you push the correct one, the scores up here a little bit, and the wrong one down a little bit, right? So you get a lot of information up from this sample, and you push the correct one up a little bit, and all the negative words down a little bit. So the next time that they see something similar, we actually do better, right, based on this data. And of course, this sounds perhaps, it's a very simplified kind of explanation of backpropagation and gradient descent. But when you do this in batches now with tons of examples, you take small steps in the right direction to be more and more wise and do better and better. And you train a lot of data, it learns to do this really, really well and build up a very nuanced understanding and capability of predicting the next word based on previous words, because it's trained on so much data, right? And of course, there are perhaps multiple sentences that start with I, when, to, with different targets, but it learns to generalize across all those different examples, right? And the longer the sequence that it trains, on gets, the more unique they get as well, right? So this is how it's trained. Very, very simple in a sense, right? But let's also talk a little bit how it's actually used now that it's been trained, right? Oh, sorry, we run this on the whole sequence, right? So we also make use of all the words in some sense in this whole sequence to use this information and the data we get as much as we can, right? Okay, so now say we want to use this, we've trained it, and we want to be able to interface with it. What we do now is that we just do a very similar thing, right? But we give the model a starting point. Here I just say like, hey, I type in I, and that will feed it to the model, right? But typically, you don't want to run your model with just an input I, right? It's not very interesting, but in this example, you just basically give the model a starting point where it should start off, right? And this is where the user can type something, but we give it I, and then it generates a distribution, again, over all possible words, right? And now, of course, there's no target, so there's nobody to help the model. So he has to be like, well, I got to pick, a guess myself. And of course, what it does basically just picks the argmax, so the most likely word. It picks the most likely word, and it puts that and adds that to the sequence, right? And then we have a new sequence and input, and we just do the same thing, right? On that input, it generates a new distribution of all possible words because there's more information, different information. And then we pick the argmax again, and we put it in our sequence, and we keep going. Right, so this is kind of very simple. One word at a time, we add it to our sequence, we make it longer, and we can run until the model predicts a period or something. So like, oh, that's the end, kind of end token, right, a period, if you just want to produce a sentence or something. But of course, what's very, like if we say we're able to do this really, really well, optimally, what's interesting perhaps is like, how can we use this now? What kind of input can we give? Because as we talked about in previous lectures, if we give it an interesting input or starting point and let it go and generate the next sentence based on that, it can be very, very helpful if it's really good at it, right? So in this, if you look at the input side here, right? Basically, input starting points here are all tasks. And if the models are able to very accurately and optimally predict the next word and generate the next sentence of this, it has to solve these different tasks, right? And the question is like, well, does it learn to do this from just training on the internet, right? Yes, it does. That's the kind of amazing part. So if you give it the input, answer this question, what is a riverbank, question mark, and let it run until it produces a period, then it will output the land at either edge of a river, right? It's quite amazing, but also that's the most sensible answer in some sense if we think about it, right? If you ask, translate to German, my name is, right, it'll output the translation because it's also the most sensible completion, right? And of course, you can do autocomplete in this sense, but it could also do classification because, if you're asking this question about, right, is this a positive or negative product review? I love this product. The most sensible output here is to generate the actual thing you're looking for in some sense because it's trained on human data on the internet, right? It behaves in human ways, so it has to replicate that. And that's, the core of ChatGPT, right? Both how it's trained and how it works. So when you type something, you just literally condition this model, and then it starts generating the next word after word until it gets to a stop token, which says like, hey, I'm done. I'm gonna now show it to you. That's how simple, ChatGPT is. But that's crazy how well it works, right? But it's this simple thing. And of course, the question is like, why is this so nice? Well, it's so nice as well because you can train on all text on the internet. There's no human being in the loop. You can just keep going, bigger and bigger models, right? So I guess one important aspect of ChatGPT is definitely its size. So it's trained in this way, but it's scaled up enormously, right? I think it has the GPT model that's ChatGPT is trained, the foundational model of it, has more than 175 billion parameters. And just in compute, like almost like just electricity bill, right? Bills, it costs $5 million just to train. So just like it basically goes through a big proportion of the internet, just trains on predicting the next word based on previous words. So somehow from the scale of it, it just becomes extremely, extremely good at solving these different tasks, right? Right, this is somehow the core component of ChatGPT. But of course, let's dwell a little bit deeper and look at more aspects. So, right, we do this now when we train this brain, basically the engine in some sense. What's kind of right? How does that engine work, and how does it play in here? And some people definitely say that the transformer part, which is the engine, the brain, is so important because it makes all the difference in some sense. I don't kind of agree, but it's definitely an important part and has been very, very useful. Right, so now we're going to talk about not the pre-training strategy, but more the brain or the model that's used, right, the engine, which is the transformer part. So basically, if ChatGPT is a car, then the driver is the generative pre-trained person, and the engine is like the transformer. All right, so when we talk about these engines and brains, let's start first talking about processing sequences, because these texts are basically sequences, right? So how can we process them in a natural way? And that allows us to understand how we can perhaps think about this brain. So let's say now we want to be able to look at this text sequence that we got from the internet, and we want to predict the next word based on the previous words in an efficient way, right? So we now get the input I as we start off with, and we let the model kind of digest that. It creates perhaps a intermediate vector, right? Number 1 here, and then it uses that to predict, its guesses on the targets, right? Then when we look at the next one, it wants to feed in the next word, which is went, right? You want to feed in that and use that somehow, and it builds a vector. But of course, it also wants to use the previous word, right? Because it wants to use as much information as possible. And we try to predict the next word based on previous words. So it also needs to kind of carry that over, right? So this also processes the previous vectors and creates a new vector now that represents both of them, right? And it uses this to predict the next target, right, 2. Right? And we keep this going. So next time, right, we digest 2 and we incorporate I went, right? So we have I went 2. And then we create a new vector number 3 here, and then we use it to predict the. And I think one thing here that's important is that when we created the first vector, we can run all the steps labeled number 2 at the same time because they don't depend on each other. They only depend on the vector number 1. It turns out that in machine learning, we have these things called GPUs, right? So basically all we care about is how many steps something run, but we don't care about something being done in parallel. If something can be done in parallel, it's a single step in cost. So we don't really care. We just want to make everything run in as few steps as possible. And if things are done in parallel, that's just a single step. So all these number 2s can be done at the same time because they only depend on the vector number 1, right? All the steps number 3 here can be done at the same time because they only depend on vector number 2, right? Make sense? So we keep this going. And we basically have now, right, 1 computational steps per input, right? We can basically use everything from before, predict the targets, and we do 1 computational step per input because they can be done in parallel. So this is how a recurrent neural network works, RNN, and it's still used, and they were used very, very a lot before transformer, and it works extremely well in some sense. But the transformer works a little bit differently. So in order to understand and to simplify this a little bit, let's look and simplify the recurrent neural network graph, right? And just look a little bit more about how information is processed or how information travels, right? Some kind of information flow. As I said before, right, this is sequential, it uses the previous ones, right? So it just starts with I, generates, pushes the information to predict the target, and pushes it forward, and just keeps going, right? In this sequential way. So this is how like the information flows in a recurrent neural network, what we just saw, right? But in a transformer, we start off in a similar way, right? We basically want to use the information of I to predict the target 2, right? But when we're at 2 here and want to predict that, we don't, we use the information, push the information from went to be able to predict the target, but we also push the information from I straight to the target, right? We don't go, we don't push it forward to went first, we just have straight edges. And same with when we're going to predict we just do straight edges to all the previous words. So somehow we just kind of ignore the sequential structure here and just have straight edges. And the cool thing here is that like since these are just straight edges and there's no dependency, we can do all of these computations at the same time. They can all be done in parallel. So this is what a transformer is optimized for, right? To do all of these computations in parallel, all these tons of edges, right? And it might seem like this is more expensive than a recurrent neural network because it has so many more edges. And it is in some sense, but because of our hardware, and because they can all be done in parallel, it's actually extremely much more cheap, because it takes a single step for a transformer to do all these computations, while it takes 9 steps for a recurrent neural network. And if you have 2,000 words long sequences, that's a lot, right? So just to kind of reiterate this, right? At target number 9 here, right? We want to predict the last word, right? We have straight edges to all previous words. These can all be done in parallel, right? But at the same time, right, we also have, when we want to predict, target number 8, we have straight edges from those as well, right? All the previous words, and they can also be done in parallel. Like all of these computations can be done in parallel. So, but this, of course, kind of to point out, this can only be done in training because we can look at all these texts at the same time. But during evaluation, we don't know the next word because we generate it ourselves, right? So then we need to do it step by step because we need to add it to our sequence and run sometimes, right? So it's still fairly fast, but recurrent networks and transformers are it's a modification, but roughly, more similar in terms of how fast they are when we actually use it. But training, it's a huge difference. But also, right, if we put them next to each other, there's much more structure in a recurrent neural network. I mean, the transformer looks very messy in some sense, right? It's like an overload of edges. So somehow, like, since there is much fewer structure and bias in transformer, perhaps we need more data to actually learn well and to be able to use this information in a coherent way, because the information is given us in this very all at the same time sense, while recurrent neural networks are given one at a time, which kind of is an inductive bias, because when we read language, we kind of look at one word at a time, a little bit at least. So it's perhaps helpful for the model to see the language in the same sequence, right? And if you think even harder about this, actually, there's nothing in the transformer that tells it it's actually looking at a sequence. We remove the sequential information. If these numbers were just for our kind of visualization, right? But this is how a transformer sees it, right? At number 9 here, it has no understanding that financial and bank are next to each other. The comes before that other one, right? Just all see these at the same time. But of course, a recurrent neural network can figure out that financial is before bank because it sees financial before it sees bank, right? So it can figure out very quickly because it's given all these words in a certain order, so the order is very clear. But transformer sees them all at the same time, so actually has no idea the actual positions and sequential information on this input. So what we need to do is to provide actually positional encodings. So for the model to be able to understand how the words relate and what the positions are, we need to explicitly give the model, we need to add to the words the position of them. So we'll know that financial becomes before bank because financial is a 5, has a 5 to it, and bank has a 6 to it. So somehow we just throw away the sequence information now and just add it afterwards to some input. And this is actually very, very strange and counterintuitive, right? Because all our text that we read is sequential, right? And we write a book from left to right, top, bottom. But here suddenly the model's like, hey, I'm just going to feed you all the words at the same time and, add a little bit number to them, and you figure it out by yourself, right? It seems like it's like you get a whole book, and you just get a messy of shuffled words, right? It's like very challenging. So it seems almost stupid in some sense, right? Similarly, right? It's like literally like you would go watch a movie and you would see all the frames of the movie at the same time. Just sit down and you see all the frames and a small number at the corner of in what order they appeared, right? But just shuffled. So what's good about this, right, is that you can sit down in a movie theater, digest the whole movie in a single frame, a second, right? And you can leave. You've seen the movie basically, but it's just scrambled and showed at the same time. So it's much, much faster, but also like how the hell would you make sense of that movie, right? Somehow to understand a movie and the plot, it's good to see them in the right order because typically that's how you make sense of it. So if that's useful as a bias to understand language and if it's frames in a movie, the model has to understand to put them in an order afterwards by itself if that's useful. But of course, maybe it's not always useful to have everything in exact sequence, right? That's the thing here. Because let's say, that if you read a book or watch a movie and only, and if you want to understand the end scene or the last, word in the book, understanding just how they correlate with the very first ones, if there's a strong connection between the start and the end, then perhaps it's very useful to see both at the same time because it allows you to see those connections clearer in some sense because it's a straight connection. But otherwise, right, if you want to see the movie or read a book from start to end, you have to remember that information through the whole movie or for the whole book, right? And it turns out that memory for neural networks is very, very hard. So the big challenge with neural networks actually was to how do you remember things? If there is this kind of long dependencies in a sequence, how do you use those and utilize those? Like how don't you forget about these things, right? So the strength of the transformer here is that yes, there's tons of edges, but there's a straight edge to all previous words. So if there is a strong signal in the data between words far away, those are distance 1 in a transformer, so it can find that signal quite fast if it has enough data and utilize that. Right, so if you want to go from the information from I to when you print the last word here, it has to go from I went to the financial bank to deposit money, right? These 9 or 8 steps. But a transformer, there's a straight edge here. So if it can learn to kind of reduce all the chaos and messiness by having tons of connections, it can also just remove all of that edge and just keep that edge, right? So it's more flexible in some sense, right? And with that being said, right, I think transformer is more flexible. And also it is a little bit of this thing where we said before, how much should we mess and encode our own human biases into these networks, right? RNN is definitely based on our own sequential, we process things in a sequential fashion. But do we really? Like a transformer is let's remove that bias and just train it on data and see if it learns it. And it does better, right, in some sense, with enough data. Right, so to summarize a little bit, so transformer is optimized to do all of these computations in parallel. For this, hardware that we use, that things that are done in parallel are just cost 1, and use positional encoding to encode the sequential structure rather than process them in a sequence. It can, since there is a straight edge between any prediction we want to do in previous words, we can utilize clone this information much more easily. So that's the strength here as well. And because of this, it replaced the recurrent neural networks. Because data, right, is no shortage, and since we can train these transformers faster, which means we can train on more data given the same compute, they actually learn to do better, right? So because of this, transformers have become the new standard. All right. All right, so now we have a language model, this transformer engine and brain trained to predict the next word based on previous words. Actually, GPT-3 was released by itself, right? It was magical and amazing how it could generate text and actually solve a lot of things for us. And it works really, really well, but perhaps not well enough, actually. It's kind of awkward in how it works sometimes. And if you want to have a chatbot interface, OpenAI tries, it's like, well, it doesn't really behave like a human being does. So we have to kind of try to push it a little bit further in a direction, right? But basically, most of the work has been done, and still people, on Twitter and scientists argue, like, how important are these next steps actually? Like, do they even make a difference? OpenAI claims so because this is kind of where they took their own route, right? But it's very questionable. But now, right, we say they have this language model, and it's a generative pre-trained transformer. Now we're going to focus on the chat part, right, which is this very, not as important add-on to see if we can make this more useful as a chatbot and appear more optimized for dialogue. So, right, maybe we're almost done, right, or almost there, but we see that this now behaves a little bit strangely sometimes when it comes to human dialogue. So we're going to optimize this now for human dialogue. So what we'll do is just that we'll focus and collect data just on human dialogues and say that GPT has been trained on all of internet, a lot of different types of language, like Wikipedia articles and stuff. But now we want it to hone in and focus on actually dialogue and appear and act like it makes sense and generate answers that have the appropriate length and format for dialogue. So we're gonna keep training it for a little bit, just a little bit, in comparison to how much we trained it before, but on this data that now is centered on only human dialogue. So we do this, and then we're like, okay, great, we've done another improvement because we let it to kind of focus and hone in on dialogue and understand a little bit. That's the kind of the more important thing here. But this is great, but then OpenAI says that, like, oh, there's some problems perhaps with this technique. We can maybe do this a little bit better even. We're now in a better place, but we can perhaps push it even further. So the problems that they identify, we'll go through now. So one thing is that when we learn from the data from the internet, right, we value all data the same. We learn blindly from the data. We don't know what's good or bad dialogue. Like, we've seen a lot of dialogue on the internet, right? Some might be toxic, harmful. Some might be useful, right? We don't know the difference. The model doesn't know the difference at all, right? And also doesn't know the difference between important and unimportant errors. It values, when it tries to predict the next word, it values all words the same. So maybe if you do like an error when you use another word as a synonym, it's not very important compared to making errors that make your answer unsensible, right? But it doesn't know the difference, and it values everything the same because it's had this like very strong, word by word supervision. Okay, next it's also that, as I said, when we have used this model, it always picks the argmax, the most likely next word based on previous words. Well, this seems perhaps too greedy, right? What we care about when we want to generate a sentence or an answer, right? We care about the likelihood and the quality of the whole answer, not just the next word, right? And a lot of times, if we just optimize short term, we're not optimizing long term. Because sometimes it's better to pick not the most likely next word, because then you can get to some higher state and a higher quality output at the very end. So what we do want to optimize is this final quality of our answer, not the intermediate ones. And there is a difference, right? We work hard and sacrifice ourselves in short term to become happy in long term, right? And want them all to be able to do the same thing. Lastly, the third problem is that, and it's a little bit nuanced, but it's been trained on all this data, right? And now that we use it, we generate the next word based on previous word, and it adds its own predictions and just keeps going, right? And of course, maybe like 10 words are not that difficult, but it generates like 1,000 words, right? And no model will be perfect, so perhaps it's going to do an error at some point, or just accumulate some errors, right? Somehow we want it to be able to, be robust to that and find itself back, because if it start generating words and it generates a small error, and it sees something that hasn't seen it in training, and it gets confused because it's very, very kind of trusting in the training data. So it's very blind to this, and it just generates an error, and it looks at its own output and is like, hey, I didn't see this during training. I don't know what to do now. I'm completely lost, and it starts generating nonsense. Right? In this example, when it perhaps start outputting its own predictions one by one, it says, I went to the financial, looks good, and then it does a small error, right? Because it's not perfect, and it says restaurant instead. And then if it just kind of gets confused, it says like to eat money, which that makes no sense. You just made this worse. So somehow we wanted to be more robust and say like, okay, you made an error, but please, try to correct yourself and find your way back into a region where you feel more comfortable. So, and that's all these things can be kind of observed in GPT, that we say like, well, maybe we can, it has these failure cases actually. How can we kind of help it out? So to summarize the problems, right? We don't know what's good or bad dialogue, right? We treat all data the same blindly. We're too greedy. We don't want to optimize just the next word. We want to optimize the quality of the whole answer or sentence, right? We care about the end quality, not individual words only. And we're not very robust because we haven't learned to self-correct, right? When we're out in the wild with users, we're gonna, do errors and small mistakes. We want to be more robust to that, to find ourselves, put ourselves back in regions where we're comfortable and where things make sense. So to address these three problems, we're gonna use something called So to address these problems, we're going to use something called reinforcement learning from human feedback. Okay, so what does this mean? Well, we'll go through it now. So we have a great model already, right? Fantastic model, actually. And people are like, well, does this even add something? I mean, people debate. But we have a great model, so we start using this very good model that we have to generate candidate answers, right? So we collect tons of prompts, and then we generate candidate answers from the model. So the model runs now in evaluation mode and generates 4 candidate answers per prompt. So if we have 1 million prompts, we now have 4 answers to each of those prompts, right? And the model is cheap. Computers can run this, so we can generate this data quickly. Okay, then we send this to human beings, and we say, now you have the prompt, and you have 4 different candidate answers. Please judge them, rank them. These are actual human beings, right? They rank, they say like, oh, this is how good this one is, and they can say, rank them in some sense, right? And provide their feedback. That's great because now we have information of what is good or bad answers, right? On 1 million examples, if that's the case, right? Expensive to get, but we have it, right? But we want more. So what we're going to do is we're going to say that, human beings, getting feedback from human beings is very expensive. So we're going to train a new robot or a computer to try to imitate those human beings, right? So now we have 1 million, prompts with generated answers that have been ranked by human beings, some score. We're going to train a robot or computer to imitate the human being giving these scores. Because, if it's able to do this well and replicate the ability of human beings to give feedback to these outputs, we can now run this on new data, right? Any data that we want to, because the robot is cheap to run. It's learned to imitate human beings, and we can run this now without having to have expensive human beings in the loop. So we can generate 100 million samples now instead of 1 million, right? Because it's much cheaper, right, to get feedback from a robot than a human being. So what we have now, right, is that we now have a robot that knows what is good or bad answers to prompts. Right? So we know now what's good or bad dialogue. So how do we incorporate this in a good way? And how do we incorporate it in a way to address the 2 other problems, right? That we're too greedy and we haven't learned to self-correct. This is we're going to use reinforcement learning to optimize and make this robot happy. So we're going to do kind of a very quick study on reinforcement learning. Okay, so in reinforcement learning, we're very much on our own. It's a lot about delayed gratification or delayed feedback. So let's say the model starts off with the input I, then it starts generating, its best guess for the next word. Doesn't get any feedback, right? Doesn't know if it's doing well or in the right direction, but it has to keep going, right? And it has to keep going until it's done, basically. Maybe it's a period, right? So it's like go until you reach a period or an end token in some sense. Then, and only then does it get a score, because then the robot looks at it, the whole output, and says like, how happy am I with this? And this one, right, is I went to a walk, period. Doesn't get any feedback, right? Doesn't know if it's doing well or in the right direction, but it has to keep going, right? And it has to keep going until it's done, basically. Maybe it's a period, right? So it's like go until you reach a period or end token in some sense. Then, and only then does it get a score, because then the robot looks at it, the whole output, and says like, how happy am I with this? And this one, right, is I went to a walk, period. I mean, it's not perfect, but at least it's a little bit sensible and it looks fairly proper. So I guess it's like a lukewarm score, right? So let's say now we run it again, on its own, and it generates a different path, and it, basically, takes, doesn't get any feedback, right? But when it reaches the end, it generates something that looks very nonsensible and very bad, and then we give it, negative feedback, so like, this actually sucks, And then reinforcement learning, right, is all about taking this delayed gratification and incorporating that to understand what are important mistakes and how do I do this better, right? Because you only get the feedback at the very end, so you don't know where you went wrong. Here, for example, both went from I to went, and in one run, it went to positive feedback, more positive, and one it was negative. And then reinforcement learning is all about figuring out how to balance this and use this to optimize the end delay, delayed gratification, which is also what we care about because we want something that's optimizing this end quality of the sentence or answer rather than intermediate words. And here it has to figure that out because we're not telling it, right? So it has to figure out what is important mistakes, what's good dialogue from just getting the end feedback. All right, another very, very important aspect that's related in reinforcement learning is exploration versus exploitation. So let's say now that we go from I to went again for some reason, and we find ourselves in this spot that we've been in before. Like, what do we do? In one way, we can say that, what we've seen so far, the computer can say, like, what I've seen so far, I know that there is one path here that's okay. If I go, I went to a walk, period, and it's better than this bad one that I've seen before or tried before. So let's say it's kind of, very greedy and exploits its information it's received so far and just goes down the best path it knows, which is I went to a walk, right? That might sound reasonable because it's seen this before and knows this is better, so at least it's going to get an okay score. But the problem is here, right, is that if it does this, it doesn't see any new data. It just sees the same data, it's seen so far and just kind of reiterates its own knowledge, right? It doesn't learn anything new. It's just, being very greedy and done what it's been doing kind of best so far. So somehow, in order to be able to learn and improve, we need to explore. We need to give up the best options that we know so far and explore something unknown because that might lead to a better solution, right? And we explore new data and we get a better understanding. That's how we improve. By exploring, we improve because if we're greedy, we just stay at our current kind of abilities, right? And I also want to say here actually that let's say, if you try to explore and have a policy for exploring, if you just randomly explore words, just, I'm just going to randomly pick the next word a few times, like that doesn't work. If you randomly pick some words in a sequence in the English, vocabulary, you're going to get complete rubbish. Like the chance you get something sensible is astronomically small, right? 99.99% of all random sequences of English words are complete rubbish. So we cannot have a policy of exploration just picking random words. So we need guided exploration, right? And the whole reason why ChatGPT can do this and use this exploration is because they have this brain that's already really good at it. And it just explores the fringes of the capability of the language model it has so far. That's why it's only gonna explore things that are kind of fairly close to things that are pretty good because it already has a very good understanding of language. So we won't spend all our time in nonsense, right? And so we talked about in previous lectures, that's like to apply reinforcement learning, you need self-supervised learning to get a good starting point because otherwise you only look at tulip, I, row, dot, right? And you won't be able to get out of that very, very bad place. All right, so by now being forced to balance exploration and exploitation, right? To optimize this delayed gratification at the very end, this model now needs to become much, much more non-greedy, of course, because we don't care about what you do in intermediate step. We only care about your end quality of your sentence, right? That's when you get the feedback. That's what you're optimizing for. And since we don't give this feedback as well in each step, because it has to learn to balance exploration and exploitation, right? It has to become much, much more robust, right? Because when it does this by itself and it gets no feedback, it probably will go off a little bit and has to find itself way back, right? Because it's on its own, it's independent. It's like literally like raising a kid and then not giving them supervision all the time, right? If you don't dote on your kids all the time, they'll probably be more independent and robust, and they'll function in the world better in some sense. And it's the same thing here, right? All right, so now we've then addressed all of these problems, right? We created human feedback, got a robot that knows bad and good dialogue. We then use reinforcement learning to optimize and change our parameters now to make this robot happy, which using reinforcement learning will force us not to be too greedy because we're optimizing the end goal. And since we're having to learn to balance exploitation and exploration by ourselves, we also get more robust and can self-correct. So we have addressed all of these different things now. Great, we'll have better performance and be much more useful, you know. But the question is now like, okay, what stops us from doing this whole thing again, right? Because now we have a better model that's able to generate better answers to prompts. So why don't we just use this on the prompts again, generate candidate answers, right? Better candidate answers, and then we get, you know, more precise human feedback on those, because now we're on a different level. We've improved. We want to have more, you know, more precise feedback at our current ability, right? We want our teachers to meet at our level. So now we do better. We want to have more precise feedback on our new abilities, and we train a new robot to mimic that, you know, more precise feedback, and then we use reinforcement learning to optimize that more precise feedback and make this more sophisticated robot happy. And that should lead to even better abilities, right? And we can rerun this process and like collect human feedback in this iterative way. So in some sense, the human feedback part is the most expensive part. That's also why we want to, you know, use it as efficiently as possible. So we can train this loop, and then we only use the, you know, ask for human feedback when we need to, and we can keep improving. I don't know how many rounds of this OpenAI does. I think it's 2 or something like that. And then we just stop when we think it's like fair enough. We don't see much improvement or whatever. All right. So to summarize, right, the whole generative pre-training is just predict the next word based on previous words, right? That's the core approach and basically most of ChatGPT. The engine, right? How important is the engine? Well, it's probably very important, but yeah. The engine is a transformer, and it's optimized to, in parallel, run all of these different direct edges, right? So this is the engine that we use to do this. And then when we've done that, we've done most of the work. That's where we spend most of our money. And then we say, let's fine-tune just on specific dialogues, because we train on data generally. And let's just look at dialogues at the very end. And when we've got that a little bit better performance, we now use this, you know, to generate candidate answers and incorporate human feedback via reinforcement learning, right? Because we want to optimize, you know what's good and bad dialogue, and optimize for the end goal of having good answers rather than just greedily each word. We want to be, you know, more robust as well. You know, when we're actually out there, you know, on people's computers, we want to be able to find our way back if we find ourselves in new situations we haven't seen before. So we use reinforcement learning to optimize this, and we can do this in multiple iterations, in some sense. All right, so some takeaways. The self-supervised learning in the foundational model here is the core, right? That's the GPT part, and it does most of the thing here. Again, as we said before, the starting point in the mental model that we really need to be able to do the next steps. And also I want to just comment on generative AI, which I think is a new buzzword that people start using. So I'm invited to a startup event later on generative AI. But I think it's kind of strange to use, because I think self-supervised learning is much, much better. Because really, I mean, it's like saying that people start talking about being able to generate language, right? And they say like, well, I don't care about being able to read language, just like writing it. But really, these are very connected. And of course, ChatGPT knows how to read language, because it gets your output and then, you know, it gets your input and then it generates the next word. So like, self-supervised learning is basically how to read and write, which is, you know, basically very interdependent things. And then generative AI is just like, well, let's just focus on the writing. And I think it's kind of misleading. So it's a little bit of a pet peeve. So I think self-supervised learning is the right word to use there. All right, in the next lecture, we will talk about Stable Diffusion, which is this, generate images conditional on text, and it creates art from human input. It's extremely, extremely useful, and it's trained in a different way. A lot of kind of connections still, and I think even perhaps more interesting and nuanced. So that'll be a lot of fun. Feel free to check out our website for more information, and thank you very much.
Can I ask a question? I have a couple of questions. Can I ask?
Yeah. Definitely.
I think the first one is what kind of feedback did you get once you're trying to generate what's a good and bad answer? So, like the human annotators, do they just tag 0 and 1, 0 and 1, or is more like a detail and nuance?
Yeah, if I remember correctly, they rank them. So they get four actual candidate answers per prompt, and then they rank them according to how well they think. So they gave 1, 2, 3, 4, right?
Okay.
With 1 being the best one. So I think that's exactly how they do it.
Another question is just so you have this like GPT model that's kind of like doing like all this sort of like work until you kind of like implement it and try to transformer. Then you said there's this reinforcement learning part, right? How do they kind of connect both sort of like models, or are they just like the same thing?
Great question, yeah. So, right, you have this giant model, transformer model, that's been trained on just the generated next word based on previous words. So that's the brain that they use in the next steps. So they just keep training it using reinforcement learning. They don't train a new model, they keep training this. So basically, right, it's like, a human being is trained, for 25 years to learn how to read, write, and, from school or something, right? And then they get hired by a news agency to generate journalistic articles, right? And they spend like the first month just like, okay, now you have your brain, right? Your understanding of text and language. I'm going to now spend a month training you to write and hone in and focus on writing good articles. So they don't throw away the previous knowledge. They use the same brain. So GPT is like this person is 25 years old and knows a lot. That's the GPT part. Then the next part, reinforcement learning and fine-tuning, that's just like the last few months, if that makes sense. But it's the same brain. It's like, so that's why it's able to do well, because it already has all this knowledge. And it's also why people like, well, actually, if you just use this first part and you put it in a chatbot, it basically has the same performance. Some people claim. I mean, just like, they're like, oh, actually, the new parts don't add that much.
I see. So, like, let me try to like reframe that a little bit. So you just use the reinforcement learning framework to sort of control a little bit how GPT, like the generative part, is kind of exploring a little bit of space and like kind of like updates a little bit of the weights inside. Exactly.
So you basically like, well, yeah, exactly like that.
I see. Yeah, so cool. Nice. That's really nice.
That's the thing as well, right? That's why even when it explores, right, it uses its own ability. That's why, like, if you're this journalist, right, to hire somebody, and they're a blank slate, right, because probably they'll write these assignments, and the editor will like, that's bad, this is good, in some sense, right? It will take a long time, but it takes pretty quick to at least get a little bit better, because you have all this prior knowledge of writing, school articles in some sense. And the whole reason why they can apply reinforcement learning is because they already have all this knowledge. That's why it works.
With doing computations in parallel, how does it know what length of the sentence it needs to write?
Okay, great. So when these are done in parallel, right, it generates, let me see if I can rephrase this. When it runs this in parallel, how does it know the length? Well, okay, depends on how you think about this, right? But that's already predefined in some sense. It has an input of 200 words. Then it has to basically encode all these 200 words in the same time, right? So it knows that its input is 200 in some sense. Let's say it has 200 words, and it wants to incorporate the embedding of all these at the same time, right? So it knows the input length. right? Does that make sense?
So it already knows what length it's going to put out.
Oh, no, so let's see if we can look at this transformer again. Okay. So this is during training, right? So now it generates one output per word, right? Because we want to predict the target of each word here. But we encode. We do tell the computer to be like, well, at position number 9, you will attend to all words, right? At position number 8, you will look at only the previous ones, etc. But when you actually, so it attends to, like that's how we encode. We basically attend to all previous words, right? They don't know the order of them, but they know they're all kind of a set, right? Just a random number of words, but attend to all of them. And during evaluation, we attend to all previous words again. But of course, we don't know how many words we're going to generate, but we generate the one at a time. So how we know what to stop when we evaluate it is by some stop token, saying like, well, when we get back a period, right, then we're not going to generate any more words. So that's how we know what to stop, basically. Does that answer your question a little bit, or?
Yeah. So before it puts out an answer, it could actually be lengthening or shortening its sentence before it decides to put out everything at once.
It never prints out everything at once. So like I said, it always prints out a word at a time. And that's the thing, basically, roughly. When it's committed to a word, it cannot change. So behind the scenes, it can explore a little bit and backtrack behind the scenes. But really, how to think about this is like, well, it'll attend to all words, it'll predict the next word, and when it's done that's final, and it moves on. Right? Use that, and it literally, it's like it outputs word by word to the user. And it's literally like it says like, I'm going to output a word now, and they're going to treat that like the user wrote that and start over. You know, so basically when you write to ChatGPT, it's going to be like, you know, what is the capital of Sweden, question mark. You write in, no, that's a bad one. How should I cook pasta, right, question mark. You type into ChatGPT. It treats this as just your input, and then it says, you know, generates the first word, you, right? It adds that to the input so far. It says like, well, now it's just going to act like it's seen that as your input. And it should. It adds that. It says like, now it looks like for ChatGPT that you said, how do I cook pasta, question mark, you should, right? And treats that as and just creates the next words. And it does that, you know, until it gets a period. Does that make sense? So it generates word by word, just saying like, well, it's literally like, the model is just like, oh, suddenly I'm getting more longer and longer input from the user, and I just rerun myself. So so it works a little bit more complicated in reality, but that's almost exactly how it is. So it is stupid in a sense that it reruns itself each time. And how it does, you know, like it is quite expensive in the sense that it has to look at the whole input again each time. Right? That's the thing actually with recurrent networks. If you have an intermediate vector, you can maybe only look at the previous one because it summarizes everything. But transformer, typically you need to look at the whole sentence again.
Just a quick follow-up on that. Like, so one thing I was a little bit wondering is like one thing that's kind of special about the ChatGPT thing in the interface is that like you can start with a question and then like the context is kind of like carried over to the next question.
Yeah.
And you can keep doing that. And like behind the scenes, how do they do that? They just like append everything and
exactly.
How do they do that?
So behind the scene, just literally make it fucking longer and longer.
Right.
So for the ChatGPT, it's like, oh, you know, it doesn't just see your last question. It just sees this whole thing as a whole long essay. That's why it can be like, obviously you should care more about your most latest question, but it's also why you can incorporate things before, because it just, and it's also why like, you know, you can have tricks here, but it's why like, it will be more, the longer lengths of history you have, the more expansive you get to generate the next word for the model, because it has to look at all the previous ones. So OpenAI have optimizations, and they probably have a cutoff as well. Like, it only look at like 5,000 words, and then it start ignoring them. So like that's why I tried sometime actually, like write, I don't know this start, but if you write like 1 million words to ChatGPT, it's gonna ignore the previous one because it's too expensive. And then maybe if you pay for an upgrade, you can do it. But that's Yeah, and that's also like, yeah, there's definitely like a lot of nuanced differences between a transformer and how, because these sequences get long and stuff, right? And you want to optimize this. So there's a lot of research that goes into how do you optimize to do this efficiently. That's also why people are like, oh, transformer is so incredible because it allows us to do this in a good way. And then people add things on this and say like, the engine is so important because it's so good at this, and what we've seen before has been fairly bad at it. Yeah, so it's very simple in that sense, right? Like, yeah, it's a nice interface, but it's literally just like, right, adding your input to, with the previous ones and just keep going, right, everything together, and just also adds its own output, right? So it also uses its own, right? It just adds everything together. So it's literally just predicting the next word based on previous words, right?
Yeah.
All the time.
That's interesting. I have like one last question actually. It's about, so you've explained like a lot like how you kind of like put humans in the loop as like human annotators. Is there any effort in kind of like using like the current prompts that are being like generated for the ChatGPT, even with the annotation, to kind of like harness that and improve it? For sure. Oh, for sure.
I mean, that's what we talked about last time. Right? That's also why they have this vote up and down. But I promise you, they track now like, does this user come back? Does he add more like to like understand if it's good or bad? Because this data is very, very valuable. And that's what we talked about last lecture as well, right? AI is so centralized and synergetic because also like winner takes all, because now ChatGPT, I mean, Google is not scared of ChatGPT because it's technology. Like, no way. They're scared of ChatGPT because it has 5 million, 10 million users in a few days. So they get a lot of data and they become the go-to chatbot. Google is like 1,000 times bigger and better than OpenAI, I mean, roughly, right? But like now they get all this data in this format and they're like, shit, they start optimizing this, getting more and more data. And then like, let's say, Google releases their own ChatGPT, like then they have to push for that, right? Because now suddenly people are already using ChatGPT, and they have to, Google has to be much better for people to switch, maybe, right? And in the meantime, ChatGPT just collects more and more data to know what's good or bad dialogue to optimize itself. So they're just kind of, taking off a little bit.
Yeah, that's nice. Like another thing that I heard in the past, I think it was like quite recently, was how kind of like this reinforcement learning by human feedback is geared towards more like generating good data instead of like focusing larger and larger models. Yeah. What do you think about that? Like, do you think it's?
No, that's a great question. So like, I mean, this is what I think. So actually, I mean, some people say like, well, 9 out of 10 researchers will work with, reinforcement learning from human feedback in the next 5 years, because we're going to have this huge model, and the only thing we need to do now is just to try to optimize and using some human feedback, right? I think that reinforcement learning is important to incorporate as aspect of reinforcement learning, because we care about the final output in some sense. We need to understand what's good and bad. But I think it's also very implicit in language. I think that there's ways to do reinforcement learning much, much more efficiently, not rely on human feedback, because what's good and bad dialogue is also implicitly encoded in the internet. I think so. I think we're able to kind of train models that's able to discern good and bad as concepts more accurately, so we don't need to have, right? I think it's implicit on the internet somehow. But definitely a lot of people say like, well, it's going to be more and more important. Some people say that actually, no, it's not that important because it doesn't add that much. I think that, and I think, it seems to me a little bit that OpenAI, I think the reinforcement learning from human feedback is like basically their add-on to like Google or like other people's work, right? In some sense, it is like a little bit their add, And they're like, well, it's very important. Like, we're so good because this is what we add to this technology. And it makes a lot of difference because they want to be like, look at us in some sense. Like, oh, we're a valuable company because we developed this approach, and it's very important. And some people, like, literally on Facebook, like on Twitter, right? People at Facebook research and stuff and go like, no, it's not important, you know, it doesn't add any value, you just took whatever we're doing. And OpenAI is like, no, it is really, really important. Like, this is what the future looks like. It will just be, you know, reinforcement learning from human feedback. So
it's kind of like overselling it.
Yeah. Okay. So I mean, who knows, right? But I think at least that I think reinforcement learning is important to incorporate. I don't think that will perhaps be as much human feedback because you can find it implicitly just in human data. And I think that the main thing with ChatGPT and what people are scared of it is because they're first and really, I mean, maybe not even first, just like they took over, and now they have, I don't know how many people, maybe there are 50 million people that use it every day. That's huge. Like, that is huge. Not, I mean, I could build ChatGPT if somebody gave me, you know, $10 million, right? Like, Google can build ChatGPT, I think, easily. But they just decide, like, maybe they probably even built something very similar, but they didn't release it because they were like, oh, we don't know how to do with this yet. It's like exploration and stuff, right? Yeah. And they probably regret that not now, right? And they probably incorporate a lot of that technology to do, right, in their Google search. Yeah. But then, of course, they're like, oh, we have people using Google, and we don't want to change the experience too much. So they do a slower progress, and then ChatGPT is just like, well, fuck it, just do a chat bot and see what people think. Yeah.
All right, thanks. Thank you very much.
Thank you, guys.
Every time a model's trained, does it increase in storage space?
Every time it doesn't, right? That's the thing.
Really?
It's because it just uses, like, basically we define a model at the very first step. That's why we're like, oh, we're gonna have 175 billion parameters, and that's what we have to work with. So somehow also, like, you know, probably potentially when we fine tune it on dialogue, it's gonna get worse at other tasks that we don't care about. It's probably gonna be worse at generating novels, right? Because it's like, maybe it's like, well, we take some of the novel generating abilities and now let it focus on dialogues only. Does that make sense? Like, with the same number of parameters, we just change the parameters how they're used a little bit.
You don't even need new hardware then every time it updates itself.
We don't need new hardware.
Yeah, you don't need new hardware, yeah.
No, we don't need new hardware. We just run it, yeah, on the same hardware. But the next ChatGPT, right, will probably be something that has 1,000 times more parameters. So when we train a whole new version, we need to have better hardware, right, and basically redo this whole thing. Okay. All right. Thanks, man.
Thank you very much.